Okay, hi everyone. Nice to see you in person. Okay, so the point of these sessions is just really just a question and answer. So you can ask questions about the course content or about the assignments or whatever you want to. Yeah, so this might be 5 minutes long, it might be an hour long. It all depends on you. So I'll just open the floor to any questions that you guys might have. Yeah, go ahead.
I do have a set of questions actually.
Okay.
First one, I'll start with how I think you briefed about how the coins are mined.
Yeah.
So if you can explain it again.
Sure. Okay, let me try and find the right part of the notes. So is it from the slides here, or is it?
Yeah, it was one of these slides and it was also the newly minted coins.
Sure. Okay, I'm just going to try and find, let's go back to this. This is maybe a good diagram. Okay, so before you understand where the coins come from, it helps understand how blocks are added to the blockchain. So I won't go over that, but I'll just briefly summarize it. So a block here means a group of transactions. So I have a transaction, I send money to you, I put it out on the network. There's people that are watching called miners, and they take a bundle of these transactions. They can choose whatever transaction they want arbitrarily. A transaction can include a fee to the miner. And so generally they would choose the ones that pay them the highest fees, right? So they're not bound to do that, but that's what they'll do. So, and blocks also have a finite size. So you can't fit all the transactions necessarily in a block. Generally speaking, with blockchains, there's more block capacity than there are transactions. But every now and then you get network congestion and then all the blocks are full. Like you couldn't even fit another transaction. There's more transactions than there's space for inside the block. So that's generally a bad thing. That means the network is congested. But anyways, okay, so they create a block. Now the way that they do it is all the miners are trying to create the next block. Why? First off is they get the fees that are associated with a transaction, okay? So they're all competing to be the person that solves the next block. So let's just assume that everyone's heard of block 13 in this diagram. So the whole network, they all know about block 13. Now what they're going to do is they're going to do that proof of work algorithm. So they're going to take all the transactions that aren't yet in 10, 11, 12, 13 that they know about. They'll make a candidate block 14, and then they'll solve the proof of work on it. So you have 100 miners, and they're all doing this in parallel, okay? One of them is going to get lucky and find the solution. When that one does, it finds the solution, it broadcasts it as block 14. And what this slide is arguing is that if you hear about block 14 and you quickly check it and make sure it's right, it's better for you to switch because you were mining on top of block 13, right? So it's better for you to just switch to 15 than to try and compete and mine block 14. Okay, but anyway, these details don't go to your question. So your question is, where does the new Bitcoin come from? And so the answer is that whoever it is that mines this block, they're given new Bitcoin. So your reward, if you're the person who successfully blocks mine 14, you get all the fees that are in the transaction, plus you get some newly minted Bitcoin. Okay, so that's, and the way it's inserted mechanically is simple. It's just you're allowed to include a transaction that pays yourself. It doesn't come from anywhere. So it's called a coin-based transaction because there's no sender. The sender is the system itself. So it's always the very first transaction, and you just pay yourself a certain amount of new Bitcoin, and that's the first transaction, and then the rest are transactions. There's no signature on the Coinbase transaction. And the question is, what amount are you allowed to write in? And so the protocol tells you. It says for the first so many blocks, you're allowed to give yourself 50 Bitcoin. And then for the next set of blocks, you're only allowed to give yourself 25, then 12, and then it eventually goes to 0. So right now we're at, I should have checked this. I always forget if we're at 12.5 or half of that. 6.25. Yeah, is that where, that's the current one, right? Yeah, so 6.25. So it started at 50 and then it halves approximately every 2 years, but it's not measured in years, it's measured in the number of blocks. And so eventually that will go to 0. There won't be new Bitcoin coming into circulation, and miners will only make profit off the fees. That's the only thing. But that won't happen for another 100 years. So it's, yeah. What else can I say? Yeah, so there's an argument that I just mentioned this. There's an argument that because miners, they're getting new Bitcoin and they're getting the fees, that maybe they charge lesser fees because they're getting the new Bitcoin anyway. And so it's possible that fees are artificially low because miners are making money off of minting. And usually they're making more money off of that than they are off the fees themselves. So as the amount that they get to mint goes to 0, then they might charge more and more fees because they have to pay for their whole operation through fees. Yeah.
Is the new Bitcoin given to the miners, is it part of the incentive pay or is it different?
Is it part of the which?
Incentive pay? Or
Yes. So the minting also helps with the incentives of it as well. Yeah.
And Professor, the
Yeah.
gas fees that we pay for the transaction, where does that go?
Sorry, say again. The
Gas fees that we pay for the transaction, where does that go?
okay.
To the miners or to the validators or to whom?
So the transaction goes to the miner. The fee goes to the miner itself. So the way a transaction fee works mechanically is in Bitcoin, you always specify an input amount and an output amount. And what you do is you leave a bit of a gap between them. And so I don't know if I actually depicted it. I sort of depicted it here. So you're like, okay, I'm going to take 3.5, it's sitting here. I have 2.5, it's sitting here. I'm going to pay out, I can pay out 6 Bitcoin, but instead of paying out 6, I'm going to send 5 to this address, and I'm only going to send 0.99 to this address. So there's 1.01 that's left over, and that goes to the miner. Now, when you send your transaction to the network, you have no idea who's going to mine, right? Because you don't know who the miner is because it's just random and they're competing for it and they don't even know it. So you couldn't write their address in. You couldn't be like, okay, pay this person, they're a miner, because you don't know which miner it's going to be. So what you do is you just leave it as sort of like money on the table in the transaction, and then whichever miner solves the next block, they're allowed to take that money for themselves.
Okay, and we also discussed that the validators also get some fees to validate the blocks. So where does that fee come from?
Okay, so I maybe conflated the term miner and validator. Sometimes when I'm speaking, I like try to use clearer language. Like mining's kind of a weird word, but miners and validators are the same thing. Or to put it another way, there is no other party that gets paid. So the miners are the only people that get paid. So if I talk about validators getting paid, I mean miners. Now, if you want to get really technical about it, there are people who sit on the network that validate transactions, but they don't mine. They're called full nodes, and they don't get paid. They just do it because whatever, it's good for the ecosystem, or they want to have the information quickly, that type of thing. Like there's different reasons why you might be a full node, and so they're considered validating nodes that don't mine. But for the purposes of this, of course, just assume that all validators mine, that they're one and the same. And so yeah, in terms of newly minted coins, that's pretty much all the details. Let me just see if there's another bullet point in the slide to mention again. Yeah, so circulation is limited. So year 2140 is when it will actually go to 0. So I don't know if any of us will be alive then. I certainly won't be. And it actually is a pretty ingenious solution because you have this big problem of if you're going to bootstrap a currency, you have to give it to someone, right? And so who do you give it to? And so later we'll see a system like Ethereum. And what Ethereum did is they generated a big pile of currency on day one. So they had a big pile of currency. They auctioned some of it off using Bitcoin, so you could buy Ether with Bitcoin. And then the people who founded the project, they all kept some for themselves. In Bitcoin's case, the founder didn't keep any for himself, although he ended up making it, but not directly. The system just started and there was no Bitcoin in circulation. The first person to mine the first block, they got the first, 50 Bitcoin, right? And then the next person to mine the next block, they got, then now there's 100 Bitcoin. And the miners are the ones that are doing the work anyways. They're like validating the transaction, so it makes sense to pay them. And so it's a clever system because it's not like Satoshi just gave him all this Bitcoin and then went out and sold it and tried to get people to buy it off of him, kind of thing, because that would just enrich him. Now it turns out he was the only one mining for the first several months because no one had heard of it. So he deployed the code, turned it on, and I don't know how long it took. I can't remember before another miner joined. That wasn't him. So he did sort of make a lot of Bitcoin at in the early days of Bitcoin. But technically anyone could have joined at that time and competed with him.
There isn't any transaction. How is validating those things?
Yeah, exactly. So what happens if there's 0 transactions? You still mine a block. So that's called an empty block. And so you do the same thing. You pay yourself, and then there's no other additional transactions. And then you put it out on the network, and then everyone starts solving the proof of work for the next one. So this system is meant to continue even if there aren't transactions. So the first Bitcoin transaction didn't happen until, I forget what block, but it was like days or weeks after the first block before the first transaction. So if you go back, you can Bitcoin's a public system. All transactions are recorded publicly. If you go back, you can see a bunch of empty blocks. Yeah.
Can you explain about public key and private key?
Sure. So I have it in the notes itself. I don't know if I touched on it here, sort of. Okay, well, anyway, forget about the notes itself. Okay, so public key, private key, yeah. Yeah.
More than one public key algorithm?
Is there more than one public key?
Yeah.
So every private key.
One is 256, another one is, for example, 512, something like that. I look at the book.
Okay. So those reference the size of the public key. And it actually references, well, not exactly the size. It's like basically the security equivalent. So when you choose what crypto system you want to deploy, you can choose a security level. So you can have public keys and private keys that are harder to break or less hard to break. All of them are thought like to be really hard to break. It's just a question of, do you want it to be secure for 20 years as opposed to 30 years or something like that? And it's all based on estimates and things like that. And you might say, well, let's just use the biggest keys, but then you have a performance hit, right? So it costs more. So people look to balance the two. So they're like, can we get a security level that we're comfortable with, but yet is okay, like in terms of performance? And so right now you end up with, these operations where the security is equivalent to, like, say 256 bits or something like that, or 512 bits. Yeah. So you'll learn more about that in 6110 and what all these numbers mean. So sometimes they refer to the size of things like the key itself. Sometimes they refer to the output of a hash function that's slightly different. In elliptic curves, it could be the size of the group on the curve. So there's a meaning behind all of these numbers. But when you pick a system, it's fixed. So everyone's private key is always the same size. And once you choose your private key, there's only one public key that corresponds to that private key. Okay, and then to go back, so public and private keys show up in cryptography in two cases. One is when you're doing encryption, and one is when you're doing signatures. In Bitcoin and blockchain, generally there's no encryption anywhere. Maybe you could add that on as a layer if you wanted to get some privacy or something. But in the basic protocol anyway, there's only signatures. So the way a signature works is I have some secret and I use it to sign documents. Think of like a PDF, okay? So I have a PDF, I have some number and I use it to sign documents. And how do you know that that PDF was signed by me? What you need is you need something that's associated with my private key. So that's called the public key. So the public key is the thing that you give out to everybody. So I give all of you a copy of my public key. And it's also important, if you want to know the document comes from me, you have to know that that public key belongs to me. Okay, so that's not obvious. It's just a number. And if someone was impersonating me, they could make up a different number and say that that was my public key. So you need to bind the two together. So in Bitcoin and blockchain, another property of it is that there's no binding between public keys and identities. So no one knows whose public key belongs to who. People might assert it. They might say, oh, that's my public key, but you don't really know at the end of the day. And you could generate lots of public keys. So this, not to confuse the earlier point, if you generate multiple public keys, you have to generate multiple private keys as well. So one secret key only gives you one public key, but you can have lots of key pairs. So you can have a lot of identities or pseudonyms that you're allowed to use. So anyway, so the public key is the thing that you give everyone. It's somehow associated with you or with the action that you want to take. So in this case, when I pay Bitcoin, I pay it to a public key. And as long as the person, that public key, the person with the secret key that corresponds to it, as long as they sign a transaction sending that money to someone else, that's what authorizes that transaction, okay? And they send it to another public key. And then the person with that, the private key that corresponds to that public key, they sign it, and then they send it to someone else, okay? So your, analogies don't really work that great. Like, if you think of a signature itself, like what your signature looks like is kind of like a public key, like people can see it. And then like the hand movement that you use to make it is kind of like your private key. Like supposedly you're the only one that can make that hand movement, although that's, questionable. And sometimes people use analogies with like locks and things like that, that are, they work better for encryption. I don't know if there's a good signature analogy, but anyways, that's basically the way it works. So your secret key is your like password kind of thing, just longer, more random. You use it to sign messages. And so when you sign a message, you take the message itself, you take your secret key, you take some randomness as well, and you generate your signature. So your signature is just a mathematical value, and you send that along with the message. So you say, here's my message, here's the signature that goes along with it. Maybe here's my public key, but we're going to assume that you already knew it was my public key anyways. And then there was some confusion about this. So I, the person signing the message, I run this first algorithm, I run this second algorithm. You, the person that gets the message that's signed, you want to know whether I signed it or not. You're the one that's going to run this third algorithm. So you're going to say, okay, here's Jeremy's public key, here's the message, and here's the value that he says is his signature on the message. And then you run the algorithm and it says, yeah, that's a valid signature with that public key on that message or not.
Professor, but in the verification function, there is any random number we are not passing. Then how they verify?
Yep. So the random number just basically means that if you were to sign the same message 100 times, you would get 100 different signatures. So it randomizes the signature a bit, so they all look a little bit different. But the verify doesn't care. It will always map. If let's say I signed it 10 times, you could put all 10 of those signatures into this algorithm. It would return true for all of them. Yeah, sure. So this is a minor point that you don't really have to worry about, but I'll try and say it again. Let's say I signed the exact same message 10 times. I'll produce 10 different signatures. Yeah, and all of them will be a little bit different because there was some randomness that went into it. Yeah. Now let's say I hand you all 10 of those signatures. You take the first one and you run verify. So the message and the public key is the message and the public key, and then you take the first signature and plug it in. It will say true. That's a true signature. Then you'll take the second signature and put it into this algorithm. So the message is the exact same. The public key is the exact same. The signature is different, but it's still a valid signature, right? It was the only difference of it is it used a different random number. And so this will return true again. So in other words, it's not just like once you fix this number and this number, there's not only one number in the universe that will return true. There's a whole bunch of them, right? But yeah, and they're basically chosen by which randomness you use. The randomness, yeah, maybe I should have just not even mentioned it. The reason I mention it is I think I discussed this at some point. If you sign the same message with the same if you sign different messages with this, let me say this right. If you sign the same message with different randomness, it leaks your private key. And so that's just the mathematics of how the signature algorithm works. There are some fixes to it, but most blockchain systems don't implement those fixes. And so it's a property that's true. And so normally you don't care because you're never going to sign it with the same randomness. But let's say you're using like some crypto wallet that you downloaded off the Android Play Store. And the developer of that app, they didn't choose good random numbers when they implemented the algorithm. So it was implemented fine. It's just they were choosing random numbers that weren't great. Java makes it kind of, there's good places to get good randomness and there's places not to get good randomness. And you have to really know what you're doing to know, where you're drawing your randomness from. Then there's a chance that you might actually end up using the same randomness twice. And so if you do that, then it would leak your private key. And so this happened in real life. There were a few times like on the blockchain where people had used the same randomness twice somehow. And it also happened with, there also were exactly wallets on the Android Play Store that had bad randomness. And I can't remember if it was this exact error, but there's other ways of attacking bad randomness. But anyways, the people lost a bunch of Bitcoin as a result of using these wallets. You also need good randomness for this algorithm. So when you choose your secret key, I think the Android thing was more related to that, which is just that they weren't choosing good secret keys. And so you could actually try every possible secret key because they weren't truly random. Yes.
Can you please explain zero knowledge proof?
Yeah. Okay, so this was something else. I think in the last question and answer, people also were confused by it. So let me say that there's not a big emphasis on it. I just wanted to sort of expose you to the idea. And so zero knowledge proof is like, I want to prove to you something, but I don't want to tell you all the information about it. Okay, I want to tell you some smaller piece of information about it. And so like the example I used last time, I think, is like, imagine a digital driver's license where all your information is encrypted. Instead of showing your birth date, like year and birthday, you could just prove that you're over 18. So even though you have an encryption of the year that you were born, you would prove that, oh, that's a year that's more recent than this particular year that was 18 years ago or whatever. And so if you were able to do that, we would call it a zero knowledge proof because you only proved the fact that you were above a certain age without revealing all of the information, which is your full birth date. So where you might use a zero knowledge proof is, let's say that you want to prove, like you have a public key. Like let's go back to that example of how do you know it's my public key, right? So I say this is my public key, but maybe I took someone else's public key and I'm just claiming that that's mine. So you could go to me and say, hey, prove to me that you know the secret key that corresponds to that public key, right? Now, if I give you the secret key, then you can go and sign transactions and you could, steal all of my Bitcoin. So I can't just give you the secret key. But could I prove to you, could I convince you that I know that secret key, I know the value that produces this public key without actually revealing that value? In other words, do I know an input to this algorithm? Do I know an input? So you know this key gen algorithm, you know how it works, yeah? And so can I prove to you that, hey, I know the input to this algorithm that produces this output, but I'm not going to tell you what that input is. I'm just going to prove to you that I know it. So that's what a zero knowledge proof is. And it's also actually what a signature is. So a signature is exactly that proof. It's basically, if you look at the details, which you'll look at in 610, for certain kinds of signature algorithms, so ones like DSA and Schnorr, it's basically a proof of, here's this public key. I know the secret key that corresponds to the public key. So that's what's giving me the authority to sign this message. And when I issue the proof, I kind of take the message and staple it to the proof. So I say, here's a proof that I know the secret key. By the way, there's a message stapled in. And so you can interpret that as I signed that message, or the secret key that corresponds to this public key signed that message. And so, yeah, so that's the relationship between them. Zero knowledge proofs show up in advanced applications of blockchain. There's two now. So one is with privacy coins, so coins that try and hide or give you stronger anonymity than Bitcoin. So Zcash is the most common example. So they use zero knowledge proofs. And the other is if you want to do things really efficiently, I'm going to retract what I said. They use something that's related to zero knowledge proof, but it actually doesn't need the zero knowledge component. So they call it ZK rollups for zero knowledge rollups. It's an optimization of blockchain to make it faster. But if you really study the details, you notice that they only use the proof component, not the zero knowledge component. So anyways. Yeah.
Is it correct if we say that zero knowledge proof is one application of commitment scheme, and commitment scheme is more general public?
Okay, so a commitment scheme is related, but I wouldn't say there's a one-to-one relationship. Actually, you can convert there's a certain kind of zero knowledge proof called the Sigma protocol that can be converted into a commitment. So there is a theoretical relationship between the two concepts. But for the simplicity of this course, they're actually separate concepts. So a commitment's just a weak form of encryption. So generally with encryption, I encrypt something, it's hidden, I give it to you, you have the power to decrypt it. With a commitment, it's the same thing. I commit to the information, I give it to you, but you need me to come back to decrypt it. You don't have the power to decrypt it yourself. So the person who does the encryption also has to do the decryption. So that's what a commitment is. And you tend to use zero knowledge with commitments. So you can use them inside the zero knowledge proof. You can prove zero knowledge is do proofs about what's inside commitments. So you're like, here's a bunch of committed data. I'm going to prove to you that this is a polynomial, and if you interpolate it, it adds up to this point or something like that. So anyway, they're often used side by side, but they're different primitives.
Could you tell about binding and hiding, and how is it related to hash function?
Sure. So a commitment function So if you hash something, it's almost like a commitment function. So generally, if I commit to something, like let's say that say we're playing rock paper scissors. You know that game. Some people don't. So like two people do like a motion like this, and they make a symbol. So it's either rock, paper, scissors, and paper beats rock, rock beats scissors, and scissors cuts paper. So anyway, the two people do it. If they do the same sign, then it's a tie. And if one of them beats the other, then that person wins. Okay. So let's say you want to play that over the phone. So you're not physically in the same room. You could do 1, 2, 3, and you could both shout rock, paper, scissors, but one of you will shout slightly before the other. And so you might have an advantage because you hear what the other person's going to do, and then you change your response. So a solution to that would be to commit to what you're going to do. Both of you tell each other what your commitment is, and now you're kind of locked into it, and you can only open that up, okay? So if we play this game with a commitment, the way it would look is I want to choose rock. So I'll take rock and I'll hash it or commit to it. I'll send you that commitment. Now, that commitment needs to have two properties. The first is if you look at it, you should know that I chose rock, right? If you look at it and you're like, oh, that's a hash of rock, and you could take the word rock and hash it and try and match it, right? So that's why just hashing something isn't sufficient as a commitment. You have to add some randomness to it as well. And so that's the hiding property that you want. And then the other thing is that if I send rock and you say paper, right, you're going to beat me. So I'm going to open that commitment up. I shouldn't be able to open that commitment up to scissors, right? I committed to rock, and so I shouldn't be able to somehow change it. And then when I open it up to scissors, because I learned that you open yours up to paper, okay? So that's called binding. So once you commit to something, you can only unlock it to the exact message that you committed to. And while it's committed, it's hiding. No one can tell what it is. So those are the two properties you want. And if you use a hash in combination with randomness, then you can achieve both of those properties. Yeah. So a hash function is binding by default because it has what's called collision resistance. So you can never open it up to some other value. Otherwise, you've broken the hash function. It's not exactly hiding because the other person can take guesses at what you might have committed to and see whether they match. And so the only way to add that hiding property is to add some randomness in that the other person couldn't brute force. Okay, other questions? Yep. Sure.
The difference between cryptocurrencies in general. We have Bitcoin, we have Ethereum, we have 10,000 odd cryptocurrencies right now.
Yep.
So is it the proof of work that is different, or the algorithm that defines the proof of work?
Yeah. Okay. So in the early days, there's sort of like maybe three categories of cryptocurrencies. So Bitcoin came out, and then what people did is because Bitcoin is open source software, you could make your own version of Bitcoin. You just copy the code and deploy it, right? And now you could call it Bitcoin 2 or whatever. And so the first generation they're called altcoins, or that generation was usually called altcoins. What they would do is, they would go in and they would tweak some parameters, usually within the system itself. So the 10-minute window of time to wait for a block, that seemed like more than enough. And so they would shrink it down to 2 minutes or 1 minute or 30 seconds, something like that. They might change the proof of work to something else. That's a more recent change, but there are some early examples where they experimented with it. They might still do proof of work, but use a different algorithm. So some of them did algorithms that were hard for you to make a circuit to implement. So the current one that's in Bitcoin, it uses a lot of hashing. You can run that on a computer in RAM. You can run it in parallel on a GPUs, or you could print out an integrated circuit that can just run that algorithm. Like it only runs that algorithm. But if you incorporate a lot of memory, then you have to store it. Then it's harder for a chip to run it because they have to have onboard memory as well, and they need random access to the memory. So anyway, so some people tweaked it for that reason. Some people tweaked it for privacy, so they tried to give it either stronger privacy or sometimes they wanted actual identities, like real-world identities. So these are some of the differences. Some of it was just marketing. People thought, hey, it'd be cool to have my own coin. And so they made it, and there was no substantial difference between Bitcoin. And so you ended up with hundreds of these altcoins. And then today, like, not a lot of them survived, right? Most of those projects are dead, but there are some that are still around. Then Ethereum came out, and so we'll talk about Ethereum, but what it does is it lets you run what are called smart contracts on top of the blockchain. So Bitcoin does to a very limited extent, but Ethereum allows you to run general contracts. So it's a very different kind of blockchain. It's a much more general blockchain. And then what you can do on Ethereum is you can create your own currencies in a smart contract. So you can have a smart contract that issues the currency. So it's on Ethereum. Ethereum has its own currency called Ether, but you could have another token that's running on top of Ethereum for some other purpose, right? So one example is people want like a US dollar. So they'll make a smart contract that issues these tokens. There's some either algorithm or just by the reputation of the company, they have a bank account with the same number of US dollars and they issue these tokens. And the smart contract just keeps track of everyone's balance. So if you want to send your stable coin, it's called, to someone else, then the smart contract keeps track of it. The smart contract is running on Ethereum, and you're paying Ether, which is the Ethereum's currency, for all the fees, like to the miners and things like that. So it's kind of a weird concept, and we'll get there and you'll see it. You'll be more comfortable when we see it later. But anyway, so those kinds of tokens you can, once again, anyone can issue. So a lot of things, like if you go to CoinMarketCap, which is a website that ranks all like tens of thousands of cryptocurrencies by how valuable they are. Some of them are alternative blockchains, like they're their own blockchain, and most of them are something that's running on top of Ethereum. They're a custom token that's running on top of Ethereum. And so that's another way that you get a bunch of these different coins. And usually those coins do something. So like sometimes they represent something. So the coin might represent a US dollar, for example. It might represent something that's one of a kind. So you might have a digital artwork, and this coin represents that digital artwork. So those are called NFTs. You might have heard of them in the news recently. Or the coin you might need it to do something like I put up a cool Ethereum app, let's say a marketplace or something like that. And to use my marketplace, you need my custom coin, right? And so you can't use it without my coin. Or if you interact with my smart contracts, I'll pay you a loyalty kind of token. Like if you go to Canadian Tire, they used to give you Canadian Tire money, or if you go to like Starbucks, you can scan a card and get points and things like that. So sometimes tokens are used like that. So if you use someone's service, they give you these tokens, and then you can come back and use them later. So yeah. So anyway, those are like why there's so many different kinds of tokens.
Professor,
Yeah.
I have a scenario-based question. So, as per my understanding, I understand that like the apps like Simple Trade and there are other apps which offer us and we can buy cryptocurrencies like Bitcoin or Ethereum. But we know that Bitcoin is 21 million in circulation in total, which are not yet mined yet. But let's say if some person comes today and say that I'm too rich and I want to buy 1 million Bitcoin. So would that transaction be approved for the person because he might want to hold that currency because it's going to be valuable in the future?
Yeah. So the any application. Okay, if you want to buy a cryptocurrency, you're buying it from someone that wants to sell it. Yeah. And so every market like that has a certain amount of depth. So there's only a certain number of people on that marketplace that want to sell. And so it's absolutely possible that if your trade is too big, that you eat up all the supply that's on the market, and then there's none left. Yeah. So buying 1 million Bitcoins, for example, is like a transaction that you couldn't, not $1 million worth of Bitcoin, but 1 million Bitcoins. So that's like, like my math's bad, but it's like billions of dollars, right? And so I don't think there's a marketplace in the crypto space that could handle $1 billion transaction. And you would also you would get a worse price. Like when you go into a market, you buy the cheapest ones first, right? But then once they're all sold out, then there's people that are asking too much money, but you have no choice because you got to buy it from them as well. So there's also the slippage, it's called. So if the more you buy, the worse you pay because you buy all the cheap ones first, and then you have to pay more and more and more the bigger your trade is. And so doing a trade of that size would also you would lose a lot of money. Just trying to execute it. So normally what people would do in that case is they would split it up into small chunks. So they would trade a little bit today and then trade a little more tomorrow, and they would try and spread it out so that there wouldn't be a big impact.
But let's talk about a time when Bitcoin was not that much expensive.
Yep.
It was not that much expensive as of now, like
Right.
5 years back.
Sure.
So at that time, I think some person might have that money or even to have that.
Yeah. So anyways, at the end of the day, every exchange has a certain number of tokens that are available for sale. Yeah. And so if your trade exceeds the amount of tokens that are for sale, it doesn't matter whether they're cheap or expensive, as long as that volume, right? It's about the volume of the trade. As long as you're doing a high volume trade, you have the chance of like just eating through the entire exchange. And so you just can't do it. And so this is true of stocks. It's not a cryptocurrency thing. It's true of all kinds of things that you might want to buy or sell in a marketplace. So yeah, and even if your volume isn't exactly say there is enough volume there, but you're eating up 50% of it, you're going to get a terrible price trying to do that. Yeah, And so it's always best to break your trades into smaller volumes and try and accumulate things slowly over time, right? It'd be the same like say I want to go and buy 1 million houses in Montreal. There's probably 1 million houses on the market, and I might get a good deal on the first 1,000, but then, eventually when I'm buying, the 900,000th place that's available, it's someone that listed it at a price that's way more than it's worth, right? But since I bought up everything else, then, I pay a higher price. I have no choice if I want to actually buy it, right? And it's also possible that there aren't 1 million properties in Montreal that are even available for me to buy. So, so it's always the same principle. The higher the volume, the worse your execution is, and then there's the chance that you wouldn't even be able to do it because there's just not enough liquidity or volume in the market. Yeah.
So you mentioned that with public address we cannot find the identity of the person.
Yep.
But with nesting attack, how they're finding the identity of the public key?
Sorry, with what?
Nesting attack.
Which attack?
Nesting attack.
Dusting?
Yeah.
I don't know that attack.
Just transferring small Satoshi coins to the to other people.
Yeah.
It's called nesting attack.
Yeah. So I know what dusting is. So dusting, like you say, it's usually when you send small transactions that are less than the transaction fee to send them.
Yes.
But I don't know how that breaks anonymity. So yeah. So I can talk in general about anonymity. So no one knows if I generate a private or a public key and I start receiving Bitcoin at it, no one knows that that's my public key. At the same time, there are ways that could be discovered. For example, if I'm using Bitcoin, I'm using it from a computer. It's an internet protocol. So I'm sending my transactions from an IP address, right? And so if you're sitting on the network, let's say you're a miner, and you see that I signed a transaction and I'm the one that broadcasts it to the network, then you might assume that that's my public key. I could be relaying it on behalf of someone else, but that would be a good indication. If I go on my Twitter profile or someone's like, I want to send you a bunch of Bitcoin and I give them my address, then you know what my address is. And even if I have multiple addresses, if I move money from one of my addresses to another one, or if I have to pay someone, I don't have enough money in this address, so I take money from 3 of my addresses and put it together to pay for something, then you can cluster my addresses together. So that's another attack where you can, if people have multiple addresses, if they ever use them together, then you can assume that they're the same address. And then if you are talking about your addresses online, then you can start to link them together as well. So you could link it to one address, you could cluster in a bunch of other addresses, and then if the IP address matches, that would give you even more information.
It's like a social engineering, gathering information about public key and understand.
Right. Yeah. So you could call it social engineering, or it's out of band. So it's not you're not getting the information from the protocol, you're getting it from all the stuff that's sort of outside of the protocol. Yeah.
So based on what you said, so let's say when there's a ransomware attack, they usually put out the public addresses for the victim to pay.
Yeah.
So how do they maintain their anonymity? Do they relay it?
Yeah. Good question. Okay, so let's make it practical. So you get one of those ransomware, on your computer and they're like, pay this address. Okay. First off, anyone can go on the blockchain and see that address. And so now there's databases where people get infected purposely and then they harvest all the Bitcoin addresses and they label them and say, this belongs to this ransomware. So that's not a secret anymore. Then if you want to know how much money these ransomware people are making, you can just look it up because it's on the blockchain. Okay. Now the problem is if you're the operator of it, how do you actually spend that money without being discovered? Okay, so if you try and move it to an exchange, the exchange will usually blacklist you or deny list you. They'll say, well, we saw that this was associated with ransomware, and so we're not going to let you exchange it. So there's these protocols called, so Tornado Cash is one on Bitcoin. They're called mixers or tumblers. And basically what people do is it's kind of like money laundering. Like a whole bunch of people put their money in a pot and then they mix it all up and then they all take it out. And so you lose track of whose Bitcoin belongs to who. And so this is either good or bad because sometimes like an exchange will just deny list everything that comes out of a tumbler, right? So your bad money goes in, maybe it gets mixed with good money, but everything that comes out is considered bad money, right? In other cases, they aren't smart enough to trace it through and realize what's happening. And so they don't associate it. They lose the association at that point. And so they don't say that that's proceeds of crime. So it's kind of a cat and mouse game where, you know, people find new ways of mixing, then the exchanges catch on, and then they start denying it. And then they find more sophisticated ways or ways that are more obfuscated. And so it sort of goes back and forth like that. Yeah. But yeah, so you can't generally, if you do ransomware, you can't just start spending your Bitcoin directly out of the account that you captured it from. You have to like go through some sort of step where you're trying to mix your money in with other money so it loses its trail. And exchanges, if you can get it onto an exchange, that's a good mixer in itself. Because if I deposit Bitcoin, like say I put $100 worth of Bitcoin on Coinbase, a day later I come back and I say, hey, give me my $100 Bitcoin back. They'll give it to me, but they're not going to give me the exact same Bitcoin, right? They're going to add it to their wallet and then I'll get back some other Bitcoin kind of thing, right? So if you can get it on an exchange, you can usually, you know, you mix it with all the users of the exchange. They're all indistinguishable at that point. Yeah. And then there's currencies like Zcash. They basically, like they have a big mixer at the protocol level. So what you can do is you can throw your Zcash into this big mix and then you can come back later and withdraw it. And then no one can tell, you know, when you pull it out, they can't tell which of it was that what you're pulling out, which input it corresponds to. So that's a protocol where they actually build that into the base layer. And then there's protocols like Monero where when you sign a transaction, what you do is you pick a bunch of random keys and you sort of say, this was signed by one of these keys, but I'm not going to tell you which one. So that's another way that you can do it as well. Yeah.
So just now you mentioned about exchanges taking a fee for those transactions, right? Isn't that what we try to avoid with Bitcoin in the first place, with having a third-party banks or?
Yeah. So that's another good question that a lot of people ask. The whole idea of Bitcoin was let's get rid of intermediaries, right? Like the banks and all of that type of thing. But then now we have like exchanges and things like that. And people realize that if you, basically there's different kinds of Bitcoin users. So not everyone has the same philosophy. So there's some people that have the philosophy of like, you should never use an exchange because that's like the vision of Bitcoin is exactly as you say. It's about self-custody is the term that they use. So you have your keys, you control your money, no one else can touch it kind of thing. So there are those people. But then there's other people who like Bitcoin just because it's convenient. You can use it 24/7. It's internet-based, blah, blah, blah. They have some other reason to like it other than hating the banking system and intermediaries. And in their cases, they're happy to use an exchange service to either to exchange it, or sometimes it's convenient to keep your Bitcoin on an exchange because if you ever forget your password, you can reset it. Or if there's ever a problem, there's a human that you can call and try and get support or things like that. Whereas if you're self-custodying and you lose your private key, or say someone makes a copy of it and steals your Bitcoin, there's nothing you can do. There's nothing anyone in the world can do for you. Like it's gone. And so it's self-custody is very unforgiving to mistakes. And so sometimes people just like having a third party. Yes, you're trusting them, but they're providing convenience in exchange for that trust. Other questions or comments? Yep, go ahead.
Regarding assignments, so when reading about the real attacks that has happened in the recent past, so majority of them didn't go into technical details.
Yeah.
So
Yeah, so your job is to try and look for different sources. Like the technical details are out there. It's just that first blog post that you read or news article, they're not going to have it, right? And so your idea is to dig a little deeper and try and find it. And in some cases, you can read between the lines and try and figure out what's going on. And you can say that in the report too. You could be like, I'm not 100% certain this is what happens, but here's a story that makes sense.
yeah, they give an overview of the technical details,
So it's going to depend on the attack. So some attacks would require more detail and some wouldn't. What I want is just like it's hard to quantify because it's going to differ from attack to attack. But just think of it like you're a graduate student in information systems engineering. Like I want something that looks kind of academic, right? Like I don't want something that like is just like reads like a New York Times article, right? Like I want some detail, and most important is that you show that you understand what's going on, right? So the detail's not there because I need the detail itself. It's there just to show that you thought deeply about it and you figured out what was happening and you really understand this attack. You're not just repeating something that you read in your own words. It's like, no, I actually understand the mechanics of how this worked. And so it's more about you demonstrating your knowledge of the attack than like, do you need the actual details and things like that. And so if it's some sort of like code, like software-based attack, I don't need like the code, like this line of code is wrong because of this. Like I don't need that level of detail. If it's some cryptographic attack, I don't need the math to show it. But I just want to see that you understand the logic of the attack and exactly what went wrong.
Professor, can
Yeah.
we go back to the scenario where there were like two versions of the blockchain?
Yeah.
That the 14th block which was added had some corrupted transaction or something, and then there was some other version. Can you please explain something about that?
Sure. So there's a couple of diagrams. I'll pick this one. Okay, so let's say that everyone in the universe is caught up to block 13. So we all agree that block 13 is the current block, and we're all happy with block 13. So there's 100 miners in our world, and all 100 of them are trying to produce block 14. Okay, one of them wins. It's just by chance, random chance. But the more computational power you have, you increase your chances. So it's like a lottery. The more computers you have, the more lottery tickets you're buying, but it's still a random draw as to who wins. So one person wins, and so they publish block 14. Okay, so they publish this one here. Now your choice is you can do one of two things. You were trying to extend block 13. So you can keep doing what you were doing. You could ignore block 14 and you can keep trying to come up with your own block 14. Or when you see block 14, you can start working. You can stop working on your own block 14 and start working on a new block 15. So that's your basic choice. So this is called a fork. Sometimes a more polite way of putting it is a reorganization when these things happen. These are like very temporary forks that happen. Usually when two people solve block 14 at the same time and they don't hear about each other's blocks. So that's another thing too. So there's a couple things that the longest chain consensus is going to solve like 3 problems for us. Okay, so let me slow down and take them one at a time. So the first one is, let's say there's an error in block 14. Okay, if you extend it with block 15, the rest of the network eventually is going to realize that there's an error in block 14. And so even though you've come up with your own block 15, they're going to throw away your block 15 at the same time they throw away block 14. And there's no way to like fix block 14 and keep your block 15, because your block 15 explicitly references block 14. So there's no way that you could just sub out block 14 with a good one without ruining block 15. So when you pick which block to extend, if you don't pick, like if there's an error in that chain up to your block and it's discovered by the network, then your chain's going to get thrown away. So you're going to lose all your transaction fees and the reward for mining this block. Okay, so your incentive is to make sure that you're only extending valid transactions.
Okay, but block 14 isn't block 14 already on the blockchain, so all will have that same copy of the ledger?
Okay, so there's no such thing as on the blockchain. So this is another thing that is subtle, but it's important. just because something's published, like just because there's these chains of blocks, nothing's 100% certain, right? Everything could get reorganized. There could be an error way back in block 10, and eventually people realize it, and then they have to redo from block 10 on. So everything in a blockchain is not 100% final. Everything's 99.9999% final, but everything is subject to revision. Okay, so no block is final, is completely final. It always can be revised. So just because someone publishes 14 and they're the first ones to publish it, doesn't mean A, that it's right, and it doesn't mean B, that maybe someone else will publish 14 before everyone switches, right? And if they publish their block 14 quickly, maybe that will become the right block 14, right? So that's the other thing. There's no right. There is a wrong kind of block, which is a block that contains an error, right? So if it contains an error, hopefully no one extends it because they will realize that they're throwing away money by extending it. So they'll all check it to make sure that it's good before they extend it. So that's the first property. The second property that happens is when you actually have two good blocks, block 14s that are produced at the same time. Now you got to choose which one to extend. And it actually doesn't matter. Like it's kind of like gambling. One of them's going to win and one of them's not going to win. So if, let me,
So all this happens in the time span of the 10 minutes in which the other block is going to be added to the blockchain.
yeah, so the 10 minutes,
Is it possible that the block is already added and it is having some flaw, or it is having a corrupted transaction?
yeah, so nothing's added with 100% certainty. So you can't say, oh, that block was added. You can just say that it was suggested. So think of it that way. So every time someone publishes a block, they're suggesting that this become part of the longest chain, right? And if the network then takes that block and starts extending it, that's how it becomes final, or it becomes added to the chain. Okay? Sorry, could you repeat your question? I just want to clarify that point.
Yes, I was saying that B14 it is having like it is containing a transaction which is corrupted.
Yep.
And the network then later realizes that there was something which was wrong. And by that time if B15 was already added.
Yeah,
So
then they'll
according to our rule of chain that the longest chain is the one which is accepted in the network. So will it not contradict with this that B14 is
Okay, good. So the rule is the longest valid chain. So in that case, it is the longest chain, but it's not valid because of block 14. So yeah, so I might not have included that, but that's the rule. So the rule is the longest valid chain. So if people realize that block 14 is corrupted, and this can happen because, like, say a miner wants to try and sneak a transaction into block 14, and maybe they discover block 14 and they don't broadcast it. Then they start working on block 15. And before anyone else has come up with block 14, they get a block 15, and then they release both of them at the same time, right? And so these are called block withholding attacks, where you try and mine a couple, like a little chain, and then you drop the whole chain, and then you try to throw consensus off one way or another. So there's something called selfish mining that uses that attack. And it's more like, it's not something I'm going to go through the details of now, but it's like a class project kind of topic to look at. But anyways, it uses the same thing. But yeah, even if the person dropped 14 and 15 at the same time, as soon as the network realizes that there's a problem with 14, they throw away 14 and 15. And they go back and they say, well, 13 was the last good block, so we got to work on a good 14. And so you could throw away a whole segment of a chain. Because there's an error. And then the other thing that happens is, like I say, sometimes two people just do it at the same time. So you have two 14s and they're both good, right? So half of the network will be working on this 14, half of the network will be working on this 14. One of them's going to get to 15 first. Okay, let's say it's the top one gets to 15. Then hopefully everyone that was working on 14 here switches over to working on 16, because that's now the longest chain. But sometimes that takes, like, say two people release them both at the same time. Half the network's working on one, half of the network's working on the other. And both of them come up with a solution to their respective chains roughly at the same time too. Then it happens again. And so you can get these, like, That's what a reorganization is when you have these forks that are like 2 or 3 blocks long before one just randomly gets longer than the other and everyone switches. And so if you look empirically at Bitcoin, I forget what the numbers are, but a reorganization of 3 or 4 blocks is like extremely rare. And I don't think it's ever happened beyond that, except for like for some software glitch or some like technical reason. There's never been just a naturally occurring reorganization of like 6 blocks.
So it will be basically caught in that 10 minutes time span.
Yeah, so yeah, and the 10 minutes also, remember, is it's not fixed. Like, it's just, I'm giving you a puzzle that takes you about 10 minutes to solve, right? And you might get lucky and you might solve it in 2 minutes. Or you might be really unlucky and it takes you 17 minutes to solve it, right? So when I give you something that's 10 minutes, it's just that on average, if I look over the past month, right, the network seems to be solving these puzzles of this difficulty once every 10 minutes kind of thing. But any given block could appear, it could appear 30 seconds later, a minute later, or it could take 20 minutes. So the 10 minutes is just sort of an average time of completion.
And what happens to the miner of B50 if he has validated
Yeah. So if you extend a block and you get discarded or orphaned, as it's called, you get no money. So it's just wasted work. Pardon?
He has already used the Bitcoin.
So you can only, so this is a great question. Okay, so let's say that we go to 13. Let me pull this down. Okay, so we go to 13, then someone solves B14, and then this person solves B15. They give themselves some Bitcoin in B15, okay? Now, they want to spend it, right? So they spend it, so they send it to someone else. Now, first off, you would need another block to actually spend it, right? Because that's a new transaction. But technically, you could spend it in the same block. They could just add a transaction down at the bottom of the transaction where they spend their own Bitcoin, okay? So they give money to you, all right? Now, what happens is people realize that 14's wrong. What I said is true. They're going to throw away 14. They're going to throw away 15. They're going to throw away the fact that you got paid. And they're going to throw away the fact that you paid someone else. So that other person that you paid, they lose, their money just disappears. It's as if that transaction never happened. Okay? So the moral of the story is, if you're looking at the blockchain and I send money to you and you're going to give me a Tesla, right? Do you, as soon as you see my transaction in a block, do you give me the Tesla and let me drive away? So the answer has to be no, because there's the chance of one of these reorganizations. So what you need to do is you need to wait to see your transaction in a block and then see a couple blocks added on. And the more blocks that get added on, the more and more certain you become that it's not going to get discarded because of one of these errors. Either it could be fraud, or it could also just be like 2 people produce blocks at the same time. So those are both valid reasons. So the conventional wisdom is that you wait 6 blocks for Bitcoin. So 6 blocks at 10 minutes a block is an hour. Okay, so if you want to be really sure, and so your wallet will show you, they talk about confirmations. So that's the term that they use for the number of blocks that have been added. So when you release your transaction on the network and it's kind of floating around, it's 0 conf. It's not been confirmed. It's added to the first block. That's 1 confirmation. Then there's a block added on. It's 2 confirmations. And then when you get to 6 confirmations, then they consider it final. Now, some, like say you go to Coinbase and you send Bitcoin into it, they might give you the money after 3 comp or 4 comp, right? Or other people might be really paranoid and they might wait even longer than 6 or whatever. So it's really your appetite for risk, and it's going to depend on how big the transaction is and other things like that. But nothing's 100% certain. Even when it's 6 blocks deep, it's still not 100% final. It's only 99.99999% final. There's always some chance that it gets reorganized.
Even for peer-to-peer transactions, is it like a 6-block wait time, or?
Yep. So all transactions are subject to the same system.
Has there been any transaction which has been lost because of a broken block? Or?
Yeah, so there have been. So there's been transactions so sometimes what people do is they do what's called a double spend attack. So what they'll do is they'll like I'll pay you in like I'll just put it out on the network so everyone can see it out on the network, and then I'll try and solve a block really fast myself, and I'll take the same money that I'm giving to you and I'll give it say back to myself. So now we have two transactions and they both can't go in the blockchain because they spend the same money, right? So one of them sends the money to you and one of them sends it to me, kind of thing. So sending it to yourself makes it sound weird because maybe both of those transactions could go through. But let's say that I pay someone else, right? So I pay you or I pay someone else. So I'm either paying one of you. I can't pay both of you. And so, yeah, what they'll do is they'll put it on the network and then they'll try and solve a block where they send the money somewhere else. And if that block gets incorporated, right, then you lose the transaction that you were expecting was coming to you because you saw it in the sort of transaction pool. And so people have done this like double spend attack in real life. But it requires the person receiving the money to not wait for multiple confirmations. So and so this was recognized very early in Bitcoin as a vulnerability. Like even right from the start, it was always advertised. But like very quickly, the community came to the consensus of waiting 6 blocks. And once they did that, it's almost never happened. If it happened, it's because of some other reason why there was a big fork. So there were a couple forks because there was some software errors. Actually, some of you might even look at it for your assignment. And in that case, yeah, the people lost money. But yeah.
Is that what they call the transaction malleability thing?
So transaction malleability is a little different. So transaction malleability is if you want to set up a chain of payments. So let's say I want to pay one person, Alice wants to pay Bob, and then Bob's going to pay Carol, and I'm going to drop both of those transactions at the same time. The second transaction has to refer to the first transaction, right? So if Alice pays Bob, the transaction where Bob pays Carol, it needs to know the identity of the first, like every transaction has an identity, an ID. And so it has to know the ID number of that first transaction because it's spending that money. The problem is that when you drop, it used to be the case, no longer the case, when you drop a transaction on Bitcoin, the identity that it's given, you don't know what it's going to be. So you can compute what it should be, but there's ways that if miners wanted to change the transaction ID on your transaction, they could do it. So so there was no guarantee. You could compute probably what your transaction ID was going to be, but if a miner really wanted to, they could change it to some other value. They couldn't choose a new value. They could just kind of randomize it. And so if you have these contingent payments, and the most important one is sometimes you have like refund transactions where it's like, I'm going to get you to sign a transaction that sends money back to me before I send it to you. But then I do it, but then when I drop the transaction where I send it to you, then the ID gets switched. So the refund that you gave me like no longer is valid because it's pointing at a transaction that doesn't exist. And so you see this in like payment networks, like the Lightning Network and things like that. And so it's a complicated thing. You'd have to read more about it. And then there were some problems too where people would go to exchanges and they would say, give me the money. They go to Coinbase and say, okay, I want my $100 of Bitcoin out. So Coinbase would issue the transaction. They would write it in a database with the transaction ID. Then what I would do is I would change the transaction ID on the blockchain. So now it's a completely different number. And then I go back to Coinbase and say, hey, I never got the money, even though I did. Like, because changing the transaction ID doesn't change the transaction. I still got the money. But Coinbase would look the transaction up and they would say, oh, like, you're right, we don't have a log of that transaction. It must not have, there must have been a problem, and then they would reissue it. And so that's how people exploited it at first. And in that case, it was just bad log keeping on Coinbase's because they weren't looking deeply for the transaction. They were just looking based on the transaction ID itself.
So if the exchange doesn't have like a good accounting system, and
yep.
then it will work well with like social engineering practices in that case.
Yeah, exactly. So it's a combination because you have to convince them that the transaction wasn't set, and then they have bad logs on top of it. And then, yeah, you put those two together and you could drain the exchange of money. Yes.
I was just reading like theoretical papers, but is there actually an implementation on selfish mining protection right now on the?
No, so selfish mining still, you could do it if you want. It's kind of a weird circumstance where it seems like the big miners just choose not to do it, even though they could do it. And I think it's because they want to keep people's confidence in the system itself. So if they started doing it, it kind of looks bad. And then maybe the value of Bitcoin goes down. And since they're mining Bitcoin, then the value of their investment goes down. And so it seems like it's sort of self-policed. Selfish mining also works really well if you're the only one that's doing it. So if there's 100 miners and you're doing it and 99 aren't, then you're taking money out of their pocket. But if all 100 of them do it at the same time, you kind of go back to the same equilibria. So anyways, yeah, so selfish mining wasn't, there's no technical fix to it, but it's one of those things that in theory could happen, but in practice seems not to be happening. Other questions? Okay, we've been here a long time anyway, so why don't we break here? And the next class will be, I think, in 2 weeks from today. Let me just double check that. If you ever want these more frequent or less frequent, we can always adjust it. But this is just based on past years that I've taught the course. The every other week seems to work well. So yeah, so the next time we'll meet is on February 22nd. All right, I'll see you all later. Thanks.